Now let's try to use hypothesis testing to see what we can say about the US population using that census data that we were looking at. So there's a link here to that US Census data, and we were looking at the October 2023 file. And before, we did some confidence intervals for the average number of hours worked in a week and for the proportion of households where someone owned a business or a farm. And so here we want to test a hypothesis about that proportion of households in which someone owns a business or a farm. So here, first we need to figure out what our null and alternative hypotheses would be. So it says we want to test the hypothesis that the proportion of households in the US in which someone owns a business or a farm is 10.4%. So we're saying something about a proportion of households, and let's say that someone comes to us and tells us that that proportion is 10.4% or 0.104. So maybe historically the proportion was 10.4%, and maybe now we want to see in October of 2023, is it different? And so we could start by having this be our null hypothesis. This is what we're just assuming is true. It's 10.4%. And if this is our null hypothesis, our alternative would be that the proportion is not 10.4%. So it's not 0.104. And these aren't the only hypotheses that would make sense. Maybe if we happen to already know our sample proportion, if it's higher than 0.104, maybe we would want our null hypothesis to be less than or equal to that value and our alternative to be greater. That would also maybe make sense, but let's just leave this at equal and not equal for now. So we want to then look at our sample and find the proportion in our sample. So in our sample, we want to find our proportion. I'll call that a P bar. That's our sample proportion. And using that sample proportion, we want to find the test statistic, which will be a z-value for that sample proportion. And so that z-value will be our sample proportion minus the proportion from the null hypothesis divided by our standard error, which will be the proportion from the null hypothesis times 1 minus the proportion from the null hypothesis all over n. And then we want to see the probability that we get something at least that far away from what we're assuming. So if I draw a little picture here, I'm thinking about z-values, and once I find my z-value for my test statistic, I don't know what that is, but that will be some z-value, and I want to see the probability that I get something that's at least that far away from the middle. So the middle would be what I'm assuming the actual proportion is from the null hypothesis. And since my alternative hypothesis is a not equals, I need to look on both sides and find the probability of getting something at least as extreme as what I got. So now let's switch over to Excel and see how we would do this in this example. So previously, we made a confidence interval for the proportion of households in which someone owns a business or farm. And when we did that, we had to find the sample proportion. And we got about 12.9%. Now we're doing this hypothesis testing. So I'm going to move down below a little bit. Now we're going to do hypothesis testing. And we're testing this hypothesis that the actual proportion is 10.4% or 0.104. So we said to do that, we need our sample proportion, which we already found. So our sample proportion is the same value we got up there, that 12.9%. And just as a reminder, to do that, We counted up the number of people who said that, yes, they did own a business or a farm, and we divided by the total number of people who responded, which was the number of people who had a value of 1 or 2 entered for them. So now we know our P and our sample proportion, our P bar, and so next we want to find our test statistic. So our test statistic is that Z value. I'm just going to make a note that this is a Z. So we said this should be our sample proportion minus that proportion from our null hypothesis divided by our standard error, assuming the null hypothesis is true. So this would be the square root of that 0.104 times 1 minus that 0.104 divided by n, which thankfully we found previously. So this n is the number of responses that we're including, so the number of people who responded with a 1 or a 2. And we got that that was 101,242, and so I'd select that value. And so this whole thing will be our test statistic. Okay, ooh, that's a pretty big test statistic. So now we want to find our p-value, which is the probability of getting something at least that extreme. So at least that far away as what we're assuming is true. So here our p-value is, our test statistic is about 26, which is very big for a z-value. That means if the null hypothesis is true, then the sample we got is over 26 standard deviations away from the actual proportion, which is a lot. And so to find the probability of getting something at least that extreme, there are a couple of different things that we could do. So I have my test statistic 26 point, I'm going to round 0.35, and I have 0 in the middle, and then I also have the negative version of this test statistic. So my p-value, I'm going to need to look at the area to the right of 26.35 and to the left of minus 26.35. And so I'm going to have 2 areas. So to find my p-value, I could first find the area to the left of the negative version of the test statistic. So negative 26.35 and 1 for cumulative. But that would only give me that left-hand tail. So to get the total area, I would need to multiply by 2 to make sure I'm also counting that area to the right of the positive 26.35. So this gives me my p-value as this teeny, teeny, tiny number. So this number right here is saying about 4.5 times 10 to the minus 153 power, which is very close to 0. And so that means if the null hypothesis is true, there's a tiny probability of getting the sample that I got. But that's the sample that I got. And so if that was super unlikely, under the assumption that the null hypothesis is true, then I don't think the null hypothesis is true. And so here I would take this p-value and I would say that's probably less than whatever my cutoff is. So alpha is what we usually call that cutoff. And we should have decided originally what that cutoff is. A common choice is 0.01 or 1%. So let's choose that. And we got a number that's way smaller than that. Way smaller than probably any reasonable cutoff. And so this means that I don't think the null hypothesis is true, because the probability of getting the sample that I got would have been so tiny. And so I'm going to reject the null hypothesis, and the null hypothesis was the assumption that the proportion was 10.4%. And so I think there's enough evidence, so there is enough evidence to conclude that the proportion of households where someone owns their own business or farm, there's enough evidence to conclude that that proportion is not 10.4%. And so if that was what was historically true, I now think that has changed. And based on our sample, I might conclude that it's gone up. And so we could do this with the assumption first for our null hypothesis that it's at most 10.4%, and try to do this to see if we can conclude that now it's bigger than 10.4%. And here we would be able to do that. And so this can help us say something about our whole population using a sample. This might help the government say that over time, we could do this hypothesis testing and say, oh, based on our current data, we think more people or more households own their own business or farm, and we can make statements about the whole population using responses to a survey like this, just about a sample.